Greetings from Madanapalli Institute of Technology and Science. I am Dr. Ashish Manna. I am working as a assistant professor at Department of Physics at Madanapalli Institute of Technology and Science. So today we will discuss about the basics fundamentals of quantum mechanics. So basically I'll give a kind of overview, or you can say the historical background, how this subject evolves from, let's say, early of the 19th century, and how it become such a important topic or subject today. And there are many applications based on the this subject. We will, in the last of the my talk, maybe I'll discuss on the application side, what are the most important and interesting applications based on the quantum mechanics, that I also try to cover. But mostly in my talk I'll discuss about the basics and fundamentals of the quantum physics, because lot of the students, whenever they are coming for the to have a degree here, UEC degree from their school level, they have the difficulty to understand this subject, because this is a completely new subject. If you can compare with the regular classical mechanics, it's a completely different subject, and so many things are there that is not obvious. So there is a chances of confusion, conflict, and many questions are there in student mind. So for in this today's talk, I'll clarify, I'll focus on all the confusion and try to develop a kind of a, you can think, a overview on the subject. So let's start our topic today. So my topic today is a photoelectric effect and wave particle duality, and from that concept of duality, wave particle duality, I'll introduce briefly about idea of electron microscopy. So the first two portions, photoelectric effect and the wave particle duality, you can think of as a basic fundamentals, all the milestone of the quantum mechanics, what do you know today. So let's start. So this is the flow chart of my presentations. So I'll first introduce these topics, then what are the, I'll discuss first the photoelectric effect, then the wave particle duality, and wave particle duality I'll discuss the de Broglie hypothesis. Obviously it will come to the wave particle duality portions, then introduction to electron microscopy, then I'll conclude. So let's start with the photoelectric effect. So photoelectric effect is a very important milestone in the history of quantum mechanics, because it is the first experimental proof that yes, quantum mechanics is real and it existed. Before that, scientists have no idea about the quantum mechanics. So all the things are there in the beginning of 19th century, all about the classical mechanics. This beautiful and phenomenal experiment came into the picture by Heinrich Hertz in 1887. So that time he discovered this effect, but that time it was unexplained, remain unexplained for many years, because of the usual thinking of classical mechanics. With the help of classical mechanics, it can't be described. So finally in 1905, Einstein came with his brilliant idea and gave a beautiful explanation of this effect, and from thereby our quantum mechanics journey will start it. And for this contribution, actually Einstein was awarded with the Nobel Prize. So that much importance is that effect and the phenomena. So what is it? Let's discuss. So the photoelectric effect is simply the ejection of electron as a result of light absorption when suitable frequency of light falls on a surface, especially metal surface. So you can see it here in the right side diagrams, cartoon diagram. We have a metal surface, let's say sodium, and we are making incident of different color lights, blue lights, then green lights, then red lights. But you can see for blue and the green one, if they are falling on the surface, electron can come out easily. But for the red light, it will not come out. How it is possible? So there is existence of cutoff frequency here that we will discuss in the few slide later. So this is very interesting. this is the peculiar phenomena or results they came about, that for any particular metal surface there is a existence of cutoff frequency. In classical mechanics, no way you can justify this answer. So you need to have a quantum mechanics to explain this answer. So in the left side is a experimental diagram, experimental setup showing you how this kind of effect can be done in the lab. So you have a tube, that is evacuated tube, vacuum is inside, and you have a anode and other side, another side is a cathode, and the cathode is actually uh, plated with the this material, this photosensitive material. So whenever this photosensitive material is exposed to light, external light, that electron will come out from that cathode. And if you have a positive voltage difference on the other side of the anode, on the other side, then this electron can come out and effectively collected through the anode plate, and you have a circuit current, so that you can measure that current and you can say I have a effective photo current. So that is a simple experimental setup. Now why you need vacuum? Because simply if you have no vacuum, there are air molecules are there, so electron may collide with the air molecule, so you don't have easily collect all the electrons. So that's why we need to have maintain a vacuum. So this is a simple experimental setup. Now we look into the very interesting results that find that this scientist Leonard and all other scientists have find out. So these results, based on this result, actually you can say the foundation and the concept of quantum mechanics what we know today has built up. These observations no way you can't explain with the classical mechanics. So what is the first observations? That this effect is immediate effect. That means the falling of light on the particular surface and ejection of electrons are almost instantaneous. There is a no time lag. In classical mechanics, whatever the phenomena is occurring, there has to some time gap, there has to some time lagging. The process has to take some time. But here in this phenomena, there is almost no time. So this is unexplained by the classical mechanics. What are the second observations? The second observation is that the magnitude of the photocurrent is proportional to the light intensity, that you can see in the figure 3. If we are increasing the intensity of the light, keeping that frequency of the light constant, the current will increase. So that also unexplained in the light of classical mechanics, because intensity, when you are increasing the intensity, that means you are increasing the energy. So how it could lead to the increase of current? So that is again unexplainable. Number 3 is that maximum kinetic energy that the electrons are ejected from the surface is actually depends on the frequency, that you can see in the figure 4. So you have a constant intensity, but if you are varying the frequency of the light, what will happen? That maximum kinetic energy that is ejected from the surface will depend, and more the frequency, more will be the kinetic energy, and that is related actually to the retarded potential. If you remember the earlier figure, you have a potential difference between the anode and cathode. If you reverse that potential, what will happen? Whatever the electron is trying to coming out, they will opposed. So at particular reverse potential, the maximum kinetic energy electron will not come out from the surface. So that is called a retarding potential. So anyway, you can assume right now that this retarding potential is connected to the kinetic energy of the electron, ejected electrons. So more the kinetic energy, more will be the retarded potential. So here, if you are increasing the frequency, keeping the intensity constant, your retarded potential will increase. So that again cannot be explained by the use of classical mechanics. And number 4, that already I have hinted in the previous slide, that there is a threshold frequency. You remember that cartoon? So there is a particular metal has a kind of threshold frequency. If the light you are using, that is the frequency of the light, if it is below the threshold frequency, then whatever the intensity may be the light, you will not get any electrons from the surface. So you have to use the light of higher frequency than the threshold frequency. Then only you can get a current, photocurrent or photoelectric effect. So that is also very interesting. So all these observations you can't explain with that time with the help of classical mechanics. You need to introduce some quantum mechanics. So this was done first by our famous scientist Einstein. Though Einstein also famous for other thing, for relativity, but here in the photoelectric effect he did a very marvelous job. So what he did actually, so he actually borrowed the idea of Max Planck. So Max Planck actually gave a very nice hypothesis that the radiations, whatever is coming in radiation or wave, they are in have of quantum in nature. They are coming like a particle. They are coming like a energy packets. So that packets or the particle light aspect of the radiation, he named it as a photon. So Einstein borrowed the idea, he took his idea and he said, here also when the light is falling on the metal surface, it actually not a wave, continuous wave. It is actually coming as a stream of particles called photon. So when photons interact with the electron on the metal surface, that electron actually have a one-to-one interactions with the photons. So each electron will absorb that whole photon energy at once, and if that energy is greater than the work function of the material, then it will be ejected out. So what is the work function? So work function, you can typically assume that it's a kind of a barrier potential or barrier energy on that surface, existing on the surface, that electron has to cover up, electron has to jump over that work potential or the barrier, then only it will come out from the surface. So it's a barrier energy, and electron has to jump over the barrier of the energy. So you have to put a certain kind of energy so that it can jump over the barrier potential. So for the sodium, it is around 2 electron volt. So whenever, let's say, I am putting some light, that light photon's energy is greater than the work function of the material, then electron may come out from the surface, and that is actually happening in the photoelectric effect. So here he gave a very nice equation called Einstein equation for explaining this phenomena. So whatever the energy is coming as a light quanta h nu, that is a energy of each photon, nu is a frequency of the light, h is a Planck constant, that you know. So if the photon energy that is coming from the source of light, if the electron is totally absorb it, then electron may come out with the kinetic energy. That kinetic energy will be how much? That is h nu, the incident energy, minus the barrier energy. So whatever is the surplus of energy, with that surplus of energy, in this electron can come out with the kinetic energy. So m is the mass of the electron and v is the velocity of the electron, that is, and a half mv square is the kinetic energy of the electron. So the kinetic energy is actually linked to the incoming photon energy as well as the barrier potential. So that's how the phenomena is occurring inside that photoelectric effect. So here, interestingly, you can see it here. If, let's say, I am putting some light such that the h nu is approximately equals to the barrier potential. So what will happen? From the equation you can see. So h nu, if h nu is almost close to the phi, that is work potential, then the maximum potential, maximum kinetic energy is 0. That means electron may come out from the surface, but effectively you can't get any photocurrent. So that is the threshold conditions. Now if you are, let's say, if I am putting frequency just below the threshold frequency, what will happen? There will be no electrons effectively. So the cutoff or the threshold frequency is beautifully explained with that Einstein equation. So that is a genius equation given by the Einstein, and that is why for this work he was awarded with the Nobel Prize. So later many other scientists like Millikan, Leonard, they have verified these equations. So it is well proved that yes, these equations actually prove the or giving you the guidelines how the photoelectric effect is actually occurring in the surface. So in the nutshell, what we can concept or what are the take home message from the photoelectric effect is that the radiations which is coming and falling on the metal surface is not actually a wave. It has a particle aspect. So the radiation what we known for a long time, that is a wave property or the wave like property it has, but now it is showing you a particle like aspect. So this is the one important conclusions that we can make from the photoelectric effect. And from this phenomena one can see in the history of quantum mechanics the actual birth or the actual quantum mechanics started from this experimental proof. So that is why it has tremendous importance. This photoelectric effect has tremendous importance in the history of quantum mechanics. So now let's move on to the next slide, that is wave particle duality. So now we know that my radiations which is wave is now actually behaving as a particle. So is it possible that whatever the particle we know for a long time, do they also behave as a wave? Is it possible? So probably the same question arises in the mind of the famous scientist De Broglie. Maybe this question haunted him, and haunted so much that he left his literature career. He actually is a student of a history. Very interesting story was there. He was a student of history. Then that time this question intrigued or haunted him so much that he started learning physics. And after that, with the certain kind of symmetry and other things, he actually gave a very nice nice hypothesis. Hypothesis of what? Of saying that yes, the particle, whatever you know, conventional particles, they can also behave as a wave. And on top of that, we can assign a wavelength for that particle, that is called matter wave. And he gave a very nice recipe connecting that particle aspect to the wave aspect, that is written here, lambda is equal to h over p. So lambda is a wavelength of that matter wave. Whatever the particle we are concentrating, for that particle, if it behaves as a wave, then the wavelength is lambda, h you know, that is Planck constant, and p is a momentum of that particle. So now he gave the hypothesis that as in the previous case we saw that radiation have a particle aspect. Now we are assuming that the particle also behave as a wave. So, and this hypothesis later proved by other experiment like Davison-German experiment, that yes, electron can also show a wave like property. So this is the tremendous, you can say, achievement, and from that actually the whole concept of quantum mechanics actually exists. So now we will see it here that we can also calculate the wavelength for many subatomic particle. Like one I have done it here for wavelength of the electron. That electron is actually under some potential difference V, and if it is accelerating with that potential difference, then what will be the lambda? So that lambda we can calculate, and if you, let's say, put some voltage around 120 volt, then you can actually calculate the lambda of electron. You see the value of the lambda, it is around a sub nanometer. So now whatever the particles which are moving, that also give you kind of a wave behavior, and that wave length of that particle we can also estimate from that De Broglie hypothesis. So now the biggest question or confusion comes from the picture. So whatever we know as particle, whatever we know as wave, how should treat them? How should I treat them? Should I treat them as a that wave as a particle and particle as a wave? So this is the point of confusion and conflict that comes for the students also and whoever is learning the quantum mechanics for the first time. This is the age long confusion. So how can we resolve this confusion or conflict? Actually there is a no conflict, it's a our lack of understanding of the subject, because it is a not obvious subject. The quantum mechanics is not actually obvious subject. You can't compare with the macroscopic things and phenomena, though classical mechanics have a one-to-one relation with our macroscopic world. We can readily verify all the Newton's law for the classical mechanics, we can readily verify by ourselves. But in quantum mechanics, whatever the results, whatever the theories, we can't verify in the normal day-to-day life, because they are almost hidden in front within in our five senses, from our five senses. So it is difficult to verify. So that is why the confusion and conflict may come in our mind. So how to resolve this? So that is why it is called wave particle duality. So whatever you know as a particle, that also give you kind of a wave phenomena. Whatever we know as a wave conventional, that also sometimes behave as a particle. So that is why wave particle duality. And you can see that famous cartoon here. It is on the internet source I have taken. So they are saying someone is carrying actually two identity, and the policeman, you can see, he is basically a simple man. He don't have an idea of quantum mechanics. So he don't know all this kind of wave particle duality business. So he only knows that one person should have only one identity. They should not have any two identity. But just now we have came up that you have the two identity, both particle and wave also. So that is why that policeman actually about to shoot him, that please carry actually one identity, not two identity. He is assuming that there is kind of a something uncanny happenings or uncanny phenomena or uncanny something suspicious happening. So that's why he is putting his gun. So now on the other side he is saying that he is very innocent, because he by nature itself he can have both duality, both particle and wave also. So now how to conclude, how to make difference and how to understand this duality. So first thing is that in quantum mechanics or in the nature, the particle aspect and wave aspect both are possible but not simultaneously. That is the first distinction. So whatever is particle, they can show the wave property but not at the same time. So you know, in the just previous experiment I have explained that radiation have a particle aspect, but that is depends on the particular situation. So in case of a photoelectric effect, the radiation actually shows up the particle aspect. But in case of a normal diffraction or interference phenomena, the light is simply light. There is a no particle aspect. So depending on the situation, it may shows up its other's identity, but not simultaneously it will show up its both identity. Similarly, a particle like electron, it will give you a normal particle light aspect, normal time, but at certain conditions, let's say in the Davison-German experiment, it will shows up as a wave. So depending on the situations, both aspect can come up in limelight, but not at once. That is the important message. So both particle and the wave aspect are possible, and they are complementary in nature. That means one time only one picture or one aspect will shows up, other will be hidden. And that is why it is also written here that at certain condition particle exhibit wave properties, and under other certain conditions wave exhibit the particle properties. So that is why wave particle duality is there. And so only take home message is from that understanding of the discussion is that both wave as well as particle aspect are possible, but they will not come at once or simultaneously. They will not shows up. Particle aspect and wave aspect, they will come in other depending on the conditions. What are the condition, experiment conditions are that there? Depending on that, it will shows up their particle or wave aspect. Next. So now whatever we have discussed, the wave particle duality, then photoelectric effect, depending on that, now I am showing you a completely different regime. I want to discuss completely different regime, that is a application of this concept. So all of you know nowadays all the research everywhere, whether you take biological science, then material science, physics, everywhere the research focus on the nanomaterials, so and the nanoparticles, nanostructures, because they have a different properties in comparison to the conventional bulk material. So all the research now is focused on the nano regime and nanoparticles. So to see the nanoparticles, to uh, guess the morphology and different aspects, sensing aspect and many others properties of the nanoparticles, you need to see them. But how to see them? It is impossible for us to have a optical microscope and see the nanoparticles. There is a no question. You can't see the nanomaterials with a normal eye or even powerful optical microscope, because the size is nano. Nano means it's a 10 to the power minus 9 meter. With the normal microscope, optical microscope, you can at most see some micron structure, but the nanometer or nano size object you can't able to see. So how can you perform, how can you see the properties or describe the properties of the nanomaterial if we don't see them? There is a way out, and the way out is a electron microscope. So that is why it is very interesting, and I will show you how this concept of electron microscope is linked to the discussion just now we have made. So it is also a microscope like optical microscope, but the difference is here we are using the electrons instead of white light or instead of normal visible light. So in the normal microscope we are using as a light, using the light to see the materials, to see the object, but here we are instead of light we are using the electrons to see the materials. How it is possible? Electron is not a wave. Electron is not a wave, it's a particle. How can you see it with electron? Just remember the idea of wave particle duality. Whatever I have discussed, that particles also sometimes behave as a wave, and here exactly that electron wave, now I am calling as a, not electron as a particle, now I am calling is a electron wave. So that electron wave I am using here in the microscopic technique to see the nanoparticles. So how can you generate, how can you generate the electron wave? Electron has to move. So that is why this is the diagram, schematic diagram showing you the, just briefly showing you the instrumental aspect of the electron microscopy. So I have electron gun, from that electron is fired, there are a couple of lenses, and with that lenses it will be collimated to the surface, whatever surface you are looking at, and from that the backscattered electron is collected by the detector, and through that backscattered electron intensity you can actually see the structures or morphology on the surface. So I'll show you a few FESM image. Of course there are plenty of FESM and TM images or microscopy images in the internet, that also you can check, they are very interesting. So I also briefly introduce a few of them. So this is the construction of the electron microscopy, and here important thing is we are using the electron wave that is coming out directly from the concept of de Broglie hypothesis. That is interesting, and using that electron wave we are actually seeing the nanoparticles. So, and this electron microscopy is very powerful compared to the your normal light microscopy that you are mostly you are using in the biological lab to see the different of cells, to see different bacteria, like that thing, small object that you are aware of. So this microscopy, electron microscopy, is way powerful than that optical microscopy. How much powerful? It is around 1 million time magnification power. Imagine that capacity, and it can show you the sub nanometer resolution object. So that's our interest. That's our interest to see the nanometers kind of object or nanomaterials. Okay. So these are the few diagram. The FESEM, that is field emission scanning electron microscopy, and